thank you all for making the trek down to come and see us today. I appreciate this. It's nice to see people in person, and thank you to those who've joined the live stream. My pleasure to introduce to you Dennis Morley, who has spent 45 years in aircraft test industry as flight tester and was retired as Chief Flight Test Engineer of BAE Systems Military Aircraft from Warton in 2015, remaining professionally active as a part-time flight test consultant who's been involved in a number of projects recently, with including the Mosquito program, Lanka as well, if you're following modern developments, as an advisor to Spirit Aerospace. So looking to talk today on unmanned air vehicles and flight testing, uncrewed air vehicles. So I think we'll join together in a warm welcome, and thank you very much for giving up your time today.
Okay, no trouble.
Thank you.
Right, good evening. As I said, Dennis Morley, career flight tester. The presentation which I'm going to give comes with a little bit of a health warning, and that is it is actually very old. It is about 20 years old. This is talking about things that we did 20 years ago. So the vehicles that I'm going to describe in many ways are historic. The testing methodologies that I'm going to describe are perfectly valid and perfectly current and form the basis of the things we were going to do with Mosquito if the MOD hadn't cancelled it, okay? So it's a bit of a story, and this is what we're going to talk about. A little bit of history of BAE's UAV programs. What I would say is that this stops with RAeS. They're up at Warton at the moment. They are doing now some new work. I am not going to cover that new work. One, because I don't know anything about it very much, and two, a lot of it's classified. We're going to talk about one particular vehicle, something got the acronym HERTI, and talk about how we tested that. So that's the flight testing part of the presentation. All right, and at the end, if there's anything you want to talk about, we can talk about things. So BAE Systems UAV programs goes right the way back to the start of this century, trying to look at the technologies and technology demonstrators that we needed in order to build the technology set to create a fairly big, potentially combat unmanned air vehicle. One of the things we were looking at was the idea we wanted a stealthy vehicle. If you want a stealthy vehicle, you don't want things sticking out of it, and therefore air data probes are a big no-no. And therefore this was flown in order to look at flush air data sensing, such that we could create a stealthy air data sensing system. So that was SORA. It was a glider, and that was stage one for the flight control system development. We then took a large radio-controlled aeroplane, bought from a model shop, and put into it the embryonics of an autonomous flying control system. That was flown around the airfield at Samlesbury when nobody was looking, and was developing quite nicely. The system that came out of that was then put into this, which is a jet-powered UAV demonstrator. Its span is about 15 feet, to give you some scale. It's a jet. It's based on the lines of a Cranfield aerodynamics project. And if you also look at the lines and look at what NASA and Boeing are proposing today for a blended wing airliner, you'll see an awful lot of similarities, because there are. It's the same heritage project line. This was a plastic plane, so it gave us some experience in large composite manufacture. It was a rapid development project. We started the engineering in 2002 and we're flying it in March 2003, which at the time we thought was pretty good going. We flew it with UK national markings on it, civil markings, and we flew it from Mackeranish on the near Campbelltown in Scotland, 10,000 foot runway, and not many people go there. So it's a good place in the UK to avoid being looked at, and also not to have many people for it to fall on if something goes wrong. And there's the beast at Mackeranish on the left, and a rather sexier shot of the aeroplane in the exhibition hangar at Warton. At this point, we wanted to create something more sophisticated, a larger vehicle, much more unstable, and we're setting about doing that when the guys in advanced studies at Warton discovered that the friends in BAE Systems Australia were also working on unmanned air vehicles. Not only were they working on unmanned air vehicles, they had got in service with the Australian Armed Forces some quite large drones, 15-foot drones, surveillance things. And in that was a flight control system, which was adaptable, had an inner loop for vehicle control and an outer loop for navigation. The two huddled heads together, and we dropped the development of the flying control system that we'd been working on, and we adopted the Australian flight control system, and that was put into the next project, beg your pardon, Raven. Raven first flew in 2003. We deliberately engineered it to fly on the 100th anniversary of the Wright brothers. Again, it's a plastic plane. The idea was it would be a low-cost vehicle. The flight control system, as we said, was stolen from BAE Systems Australia, and we put the Raven model into the Australian flight control system kernel. It's highly unstable. It's got a set of lines that we developed with RAE, and therefore it was quite a complex design and control law problem. 9 months from starting to flying the aeroplane in Australia, and we were quite pleased with the results. We flew it for several months as a demonstrator. The idea was this was to be a kernel for development of future vehicles. So if you look at it, at the aeroplane, it has a central body and wings. The idea was that by taking one set of wings off and putting another set of wings on, we could go from something which was representative of a combat air vehicle to something which is whoops, go back. I'm pointing at the screen and the receiver's over there, silly boy. By putting on wide-span wings, we could create something which would be a long, high-endurance vehicle, pressure range equation and all that stuff. A high aspect ratio gives you a longer airborne trial. So the middle of this is the same corax element, but the outside are the two wings. And for what it's worth, that was Chris Allen's aeroplane when he was at Warton. Okay. And we flew that the following year in 2004. We recognized that there was another place in the market we might want to go to, and that was lower end, low speed vehicles. So we did another demonstrator, HERTI. Now, HERTI, high endurance, rapid technology insertion. It's an appalling acronym, but it's the one we were stuck with. It's a concept demonstrator. We didn't develop the airframe. We bought the rights to a Polish motor glider, and it was made out of fiberglass. The idea was that if we went into production, Slingsby's in the north of Yorkshire would mass produce these things for us out of fiberglass. Inside it is yet again the Australian flight control system, but this time with a HERTI model inside it, so that we're not redeveloping the flight control system, just reprogramming the bits inside it that revert to the aerodynamics and the handling of the vehicle. As we say, it's based on a Polish motor glider, 8 meter span, so it's about a 28-foot aeroplane. The idea was to do this very quickly, and the guy in Poland had got a spare airframe, so we stole it basically, and we put a little jet engine in it because we wanted to see whether or not we could make a jet engine. It only had the one wheel, and it worked, and we flew, and this beast flew quite effectively. And there we are flying from Australia at the range at Woomera. The performance of this vehicle wasn't what we expected. It was determined that actually a jet was the wrong propulsion system. Wouldn't it be a better idea if it was propeller driven because it was a low speed vehicle? And therefore, with the next airplane that we produced was a derivative of the first HERTI design. This used a larger version of the Polish motor glider with a much bigger span. It had a simplex flight control system. So immediately there's an element of risk. You've not got redundancy. We put a BMW motorbike engine in it, and the chief engineer promptly had away with the rest of the motorbike. It was about 125 knot aeroplane. And from the first flight, we put a very sophisticated reconnaissance system into the vehicle so that we could dual develop a reconnaissance system and a vehicle in parallel. It was accepted if we lost the vehicle, we would lose the reconnaissance system. And that flew in 2005 from Macranish, initially in Scotland, and was very successful. That led us to spend money on developing a more sophisticated version of this vehicle, 31B, which now has, this aeroplane, because it had simplex flying controls, had a recovery parachute. So if we lost control of the vehicle, we would fire the parachute and the parachute would force the aircraft down to earth, okay? And that was a way that we could enhance the safety argument for a simplex aeroplane. 31B, we put duplex flight control software into the aeroplane, and therefore we could dispense with the weight penalty or the drag penalty of the parachute. We put an aircraft quality aero engine in, a Rotex aero engine, and we ran an extensive series of flight trials with this aircraft and actually went as far as market testing it with certain foreign customers. So this is the aircraft that we're really going to concentrate on today and talk about how we went about managing the flight test program so that we make sure the hole in the ground is where we want it to be. Could I ask you a question at this point? In the audience, how many of you are ex-missile people? Okay, and you've been around test and evaluation, so you know about ranges and safety and all that kind of thing. Okay. It's at this point you might as well take over because I'm stealing your thunder. No? Okay. The Royal Air Force took the aeroplane to Afghanistan and actually used it to look for improvised explosive devices. They were reasonably successful with the aeroplane. They took out 2 and only brought 1 back. It wasn't because there was anything wrong with the vehicle, but a Hercules blew the other one over at Kandahar. We took Herty and we armed it. And we put, it's the opposition's devices, some Thales man-mounted weapons onto it, took these to Australia, and using the, I'm going to talk about it in more detail, but there is a turret-mounted camera underneath the aircraft. We co-located that with a laser and tried to turn it into a poor man's target designator. So the idea was this would shine at a pickup truck, which was going to be the target. We'd shoot the weapon and try and hit the pickup truck. We didn't hit the pickup truck, but we did hit Australia under guided control. And as it was an experimental program, we sort of counted that as a success. But that was the first example of anybody arming a UAV in this country. And again, this is about 15 years ago now. Then we went for a biggie, twin-engined, 90-foot span, representative of a large I-Star vehicle. Again, rapidly prototyped. It was 2 years from starting to commissioning to flying the beast in Australia. It proved conceptually that we could handle also a big aeroplane. And yet again, it's got the Australian flight control system in it, just with a different aircraft model. So we really were levering what the mates in Australia had actually developed for us. In order to support this, we had a research jet stream. So before we put systems into the UAVs, we would fly them on our research jet stream. It had a luggage pannier underneath, which is really good for putting various bits of kit in. It's been retired now. We had 2 of them, in fact, over a period of about 15 years. This acted as a surrogate UAV, and so we could have two crew in the front who were completely hands-off. We can have effectively a UAV in the back of the aeroplane, which was flying the aeroplane, and we flew a surrogate UAV profile all the way up the country under CAA control using this to try to demonstrate how we could integrate UAVs with civil airspace. And the last thing we did, which is very different now from the others, is RAeS. RAeS looks a lot like Raven. It comes from the same historic lengths, sets of lines. Raven was about a 12-foot aeroplane. This is a 30-foot aeroplane. It's the weight of a Hawk. It's got a Hawk engine in it, a Hawk-a-Dua, and is fully representative of a big combat UAV. It's got a small weapons bay in it, so we could carry stores if we needed to. Unlike the French Neuron program, which was very much about systems development and demonstrating what these things could do in an operational context, this was a program about demonstrating an unstable, stealthy air vehicle. You'll notice this is the prototype aeroplane, and therefore it's got a probe on it. So for the initial flying, we fly with an air data probe. We use that to calibrate the flush air data. We then take this off because it makes the airplane very, very unstealthy. This aircraft was flown against a very calibrated radar in Australia. And what do we say? We say that the Ministry of Defence were exceptionally pleased with the results. We never took this to production, but the techniques and technologies that are in this are now going into Global Air System and the Tempest aircraft in terms of signature control and signature measurement. So that's the quick canter through the things that we did some 20 years ago. We're now going to talk about 30 flight trials in a bit more detail. So 31B, this is the kind of things that we were trying to do. We've got a 13-meter airplane, so it's a 30-foot span aircraft. It's about 16 feet long. If you were flying it with a pilot in it, you know, it would be a performance glider and could soar and things like that. Target altitude was 20,000 feet. Endurance target altitude was 25 hours. The limit to that generally was not fuel, it was oil consumption on the Rotex engine. Radius action, potentially 1,500 nautical miles. A variety of sensors, electro-optic, infrared. This autonomous imagery collection and assessment system, a bit more of that in a moment. An autonomous flight control system, which is now working with the Australian flight control system, which has got the ability to be told to do stuff. So you would tell it, go and find something that looks like this. And it would then institute, when it went into the search area, its own search pattern, looking for stuff that looked like that. When it did, then it would notify home base, I found something I think you want to look at. So the first part of the processor was automatic. It also had the ability to fly around simulated guided missile threats. So whilst the aircraft was airborne, we could upload to it the latest effectively hostile picture, and the vehicle would then moderate and change its flight plan to avoid what would have been a hostile air defense system. We operated both off paved and grass runways, just so we demonstrate we had, but normally we operated off a paved runway. So this is the aeroplane. What we've said, we've got a Rotex aerospace quality engine. We've got global positioning system antenna on both wings. So we've got GPS duplex receive. We've got duplex command link antennas for talking to the ground. so that we've got space diversity and frequency diversity in terms of command links. We've also got a data link aerial. The data link transmits the information from the payload and the wide field of view cameras and the fixed turret camera under here. We've got a forward-looking camera because throughout all of these trials, we did keep the potential for a man in the loop. So one of the things that you'll see we had a guy who, if things were going really pear-shaped for us, could take control of this as if it was a large radio-controlled aeroplane and could bring it back. Okay, that was something we did for all of our aeroplanes, including Taranis. We had a big debate with the pilot community about who was going to fly it. We did various trials in the simulator with the pilots trying to fly it. And we also had a lad from the hangar at the south side of the airfield who was a radio control champion. And every single time he was better at bringing the aeroplane back than the pilots were. So guess what? We finished it with our radio control champ as the recovery pilot if anything went wrong. And there were 2 occasions where we actually reverted to manual mode and brought the aeroplane back in situations where we probably wouldn't have recovered it in autonomous mode. Got a high aspect ratio wing for long endurance. We've got proper brakes. It's altogether becoming a much more sophisticated and capable vehicle. Talk about the ground control station. Obviously, the vehicle is programmed before flight with what we expect it to do. In flight, there are various things we want to do. One, we want to monitor what it's doing, because if we don't know what it's doing, it ain't safe. So there are some screens where we've got a system operator who's looking at the performance of the vehicle. We've got another screen, which is the UAV pilot, and he's looking at a completely different set of data. He's looking at a pseudo flight control display. The film image has been taken by the forward-looking field of view camera, such that he can fly the aeroplane when it's close to the ground and close to the airfield. We have a flight test engineer who is in control of the testing of the aeroplane, and effectively during the flight is taking advice from these guys and deciding, yes, we will continue with the sortie. These are the things that we are happy with, stuff like that. Independently from that, we have a representative from the Australian government who's got a big red button. And if at any time he is unhappy with what we're doing with this thing over Australia, he has the wherewithal to press the big red button, which will bring the aeroplane crashing down to earth. Okay. We also have at the back the UAV commander, the sortie commander, generally a test pilot who is looking at the flight from a flight control and airmanship point of view. And he's the other person in the room who can command the safety officer to press the red button. So these 2 guys have got cut down authority. These guys are flying the aeroplane, and this guy brings it back if something goes wrong. Okay, that was the experimental setup. That's what it looked like. It was just a set of screens in the control tower at Woomera. The early development trials, as we said, were a UAV commander, the test pilot at the back, a flight test engineer who was managing the test sortie, a vehicle systems operator and a vehicle systems specialist who were generally driving the vehicle and looking at what was coming back from the vehicle, the UAV pilot for reversionary control, a payload operator who was driving the intelligence system in the vehicle. And interestingly, they were 2 floors below us in the control tower, looking at a completely different set of reconnaissance screens. A lot of the time, we didn't know what they were doing. And the range safety officer. We realized that was getting a bit busy, so we combined some of the roles. And actually, for an operational vehicle, we reckoned it could be done with a team of 3. And the UAV commander could probably oversee several sorties at the same time. Command and control, we're in the control tower at Woomera. We manually taxi the aeroplane. So this is the radio control guy, taxis the aeroplane to the takeoff point, at which point he hands off back to the control room, who put the vehicle into autonomous mode, press the go button, and that's it, it's off. We now should be completely hands-on throughout the whole mission. It flies through several phases of flight. So takeoff and climb out is the first phase, and that's one set of laws for the aeroplane. With something we call scenario, that's when it's bumbling around on the range and doing whatever it is we've told it to do. Then we enter circuit mode, which is coming back from scenario. Takeoff and climb out is relatively low level, obviously. We then get to operating altitude and we'll be 5,000, 10,000 feet in scenario. Circuit is where we return at 15,000 feet and spiral down to an approach altitude, where then we do approach, lining up, making sure we're happy with the runway, and actually the landing phase itself. And clearly, during takeoff, until we're weight off ground, we're in ground laws. When weight off ground micros operate, we go into air laws, and similar on landing. We change from air laws for the approach and the touchdown into ground laws once we're on the ground. And we can, at any time during the sortie, tell the vehicle to do other things, like loiter, at which point it will just do an orbit. Or if something's really going badly wrong, go and crash yourself safely at the far end of the range and we'll come and get you later. Command and control system schematic, therefore. For navigation, we're using GPS. For altitude, we're using GPS inertial, we're using baro, and at very low level, we use a laser altimeter. So the takeoff and landing phases are actually driven as much as anything by the laser altimeter. And in fact, one of the reasons we had a quite serious bouncy incident once was because the laser altimeter went broken on us. We have upper and lower command antenna, which allows the ground station to send flight commands. We have a vehicle monitoring system, which is built into the downlink from the cameras on board the aeroplane. So we've got two ways of talking to the aeroplane. And this one will tell us where it is. It will also allow the UAV pilot to take control if the standard command link goes wrong and things like that. And if all else fails, red, we press the red button and bring the aircraft down. So we went to Woomera. Why did we go to Woomera? Various reasons for going to Woomera. We didn't want anybody, the Americans were very keen for us to go there and we didn't want to do it in America. The South Africans wanted us to go there and we were very keen not to do it in South Africa. The Swedes wanted us to go to northern Sweden, but they can only fly for half of the year, so they were out. And the Australians, clearly, they'd given us a flight control system, and the mates in BAE Systems Australia said, you really should come to Woomera because it's such an easy place to do test flying. It's private, it's pretty EW secure, it's amazingly inexpensive once you've got there. And it is absolutely enormous. So you've got a pretty free hand on things that you want to do. So giving you an idea about the scale of the place, here's Australia, which is a big place. It's 3 hours from there to there in an aeroplane. So this is the Woomera test area in the middle of the country. And this is it starting. It's about 5 hours by car north of Adelaide. It's where the original rocket trials of Hawker Siddeley's Blue Steel were carried. Blue Streak, and Blue Steel for that matter, when I think about it. Blue Steel was shot on the range as well. And Bloodhound and all sorts of things were shot on the range at Woomera. But most important for us, it was a really easy place to set up safe, sterile areas for testing something where we were a bit uncertain about how it would behave. So getting there, there's the great luxurious bit where they fly you out to Australia with Singapore Airlines. and then the rather more down-to-earth bit where you have to carry your own luggage to the Saab aeroplane, and then the long drive from the airfield at Roxby Down down to Woomera. One of the first things they do is brief you about the fauna. The Aussies have great fun with this. And one of the first things they tell you is, don't worry, mate, there's no two-step snakes around here. Well, what do you mean by two-step snake? Well, it bites you, you've got 2 steps and you're dead, mate. But they're all up in Brisbane, they assure us. They do have Western Browns, 4 of which are none, which are large, about 8-foot snakes when they get to be quite big. And apparently can spoil your day if they bite you. So that's some real fauna, just to prove we've been to Australia. And that's what Woomera looks like. This is the perfect test area for things that might go whoosh or bang. Woomera Range itself, there's a big hangar that they gave us that was our hangar. Well, they say they gave us, they didn't tell us about the redback spiders in one corner of it. And one morning we came out to find a Western Brown coiled up next to the aeroplane. We said, well, what do we do? And so we'll just ignore it and it will go away, and it did. So that's the various ranges where you can go and have reconnaissance targets or attack things. And that's a view of our aeroplane on the air apron with the runway out here. It's a long runway, about 8,000 feet. The Royal Australian Air Force operate F-18s out of there routinely. Full hangar, workshop facilities, air conditioned, really, as flight test places to go, it's not bad. There's also a gravel runway, which the Americans have rather churned up with a C-130, but we actually did some work off the gravel runway. And the really good thing about it is bottom one. It permits you to go straight off the end of the runway and you are in the range area. So there's no transit phase from an airfield to the range. The airfield is inside the range parameter. The trials philosophy, and anybody who works with missiles will know this, is test safe. So we assume from square one, this thing is going to crash. All we know is, we don't know is when. And therefore we will operate this vehicle such that when it fails, no matter how it fails, we're not going to hurt anybody. There'll just be an expensive hole in the ground. So that's, and as part of the rapid prototyping nature, we accepted we might finish up with a hole in the ground, but we also put some very expensive assets onto the vehicle so that we could shorten the overall test cycle, which proved very successful. We're operating in a sterile area. The only people that are in the range area, there are sheep herders, and the Australian liaison people would advise, when we were going to fly, they'd go and advise the people who'd got the sheep what it was we were going to do, where we were going to do it, when we were going to do it, and so they could get the sheep out of the way. We said, how on earth do you get sheep out of the way? Said, well, you just move the water and the food and they move out of the way. So they sort of that. There were also some Aborigines, and there was an Aboriginal officer who liaised with them, and they generally, they did not move. We worked around them in terms of where we flew. So, as we say here, all flight testing is controlled by use of a debris line and a cut down line. There's a picture. The debris line, let's go to the picture. The debris line, let's talk about the picture. This is the little bit of the range area that we were going to use. If you imagine the total size of Woomera, it's about the size of this wall. That's how much of the range we're using. It's a small area. Driven as much as anything by the radio range, visual horizon from the aerials on top of the control tower. So that's that arc. There's a range road that runs up here to go to the missile launching center, and therefore we put our debris line inside that road. There are some very expensive gamma ray telescopes, so we avoid those. The airfield's down here. The road that goes to Roxby Down goes up here. So that gives us our next debris line. So the red line is the area in which, no matter what happens, the junk is going to land inside that line. Obviously, we're operating at altitude. If something goes wrong, the vehicle can travel a distance. And therefore, we also establish something we call the cut down line, which is inside the debris line, such that if the vehicle is going wrong, we cut it down here, it can't get beyond the red line, okay? So really, our test area becomes the cut down line, and depending on the altitude you're operating at, the cut down line is a variable feast, and we calculate that in real terms. So if you're very, very low altitude, the cut down line can be very, very close to the debris line. If you're at high altitude with a lot of wind, the cut down line is a long way away from the debris line. So that's the area. So here we have basically the maneuver area that we played in, the transit area for getting there, and the circuit area when we go into circuit mode. In mission planning considerations, that's what we've just been talking about. The vehicle is autonomous when it gets into its mission. Now, have I got a better picture? Yes, I've got a better picture. So this is the typical kind of planning profiles that we'd use. We would take off and we would climb using a spiral to test altitude. We would then enter effectively whatever route we'd programmed the vehicle we wanted it to do. On its way to the area where we wanted it to be operational, we could give it pop-up threats. And what we wanted it to do at this point was deviate from its pre-programmed flight path and fly around the pop-up threats, which it did. We then have this, which is really the flight area for the main act. The vehicle enters this and goes into its autonomous mode of search. You've told it that within these two circles, there is something. Here are its characteristics. Go and find it. One of the things that guys programmed it to do was to find a sheep. And whilst there are millions of sheep in Australia, there is a lot of distance between sheep. So they programmed it to find sheep. And when we told the Royal Australian Air Force we'd successfully identified a sheep on the Woomera Range, they just fell about laughing on the ground. They didn't think that was a great thing. So we actually said, well, can you just put something else out in the range, a pickup truck, an old tank or whatever, and we'll go and tell it to find that, which it quite successfully did. So that's the kind of mission testing we were doing. Before we went airborne, we would do a hardware in the loop practice. So we'd tie the vehicle down, fire up the engine, and run the aircraft as if it was airborne, with various airspeed stimuli, things like that into it. And the crew, the command crew in the control tower would be operating the vehicle. And for the purposes of this, because they'd not got anything better to do, the data link people who would have been looking at the reconnaissance features, they were 2 floors down, inventing faults that they could throw into the system so that we could exercise emergencies. So we would fly a profile and we would have simulated emergencies thrown at the guys in the attic who didn't know what was going to happen in order to prove that we were ready to aviate. And that was very successful. That was very successful. I say, planning for an emergency, we went for graceful degradation. And therefore, the first thing we do is, if we've lost contact with the vehicle, just leave it in autonomous mode, because there's a very good chance it'll start talking to you again a little bit later on in the mission. It could be an aerial aspect issue or things like that. If that didn't work, then command it to circuit mode. And when you command the vehicle to circuit mode, it basically is a come home command. And we've got two ways of getting a come home command to the vehicle, one on the command line and the other on the data link line. If the vehicle's coming home and we're not comfortable that the automatic system is flying the vehicle, at that point, the UAV pilot potentially would take control and fly the aircraft back to the airfield at Woomera. If that's not working properly, we've got the option of diverting the vehicle to an alternative landing site elsewhere. It probably would finish up as a crash landing, but it would be an autonomous landing and we get the vehicle back. And the last thing we do, if something's really going wrong, is press the big red button and terminate the vehicle. Interestingly, during trials, there were a number of, so you're watching the vehicle approaching the debris line. And the hard rule was, if it crosses the debris line, you cut it down. People were watching what it was doing. And what it had done, we wanted it to turn, and we all expected it to do that. It didn't, it did that. Why? Because the automatics and the autonomous said, rather than turning that way, I will execute a left-hand turn by doing that. That turn took it outside the debris line. Technically, both the range control officer and the UAV mission commander should have called, put it down. Both of them had a quick chat, concluded, no, clearly this vehicle is conducting a perfectly controlled maneuver and is heading back in a safe direction. We shan't. And so even over the top of those hard roles we established, there was still a level of discretion where human judgment was fed into the middle of things that were going wrong. The flight termination system, as I said, in the initial stages, we had a parachute. On this vehicle, because we've got duplex channels going up and we've got duplex flying controls, we're pretty certain it will do what it's told to do when we say cut down. And what it does is it stops the engine, so it's become a glider. It applies full nose up, full right yaw, which are clearly pro-spin controls, and throws out both air brakes. All of these things clearly are going to put this aeroplane in an attitude where it's going to descend very, very, very rapidly down to the ground. And if we press the button on the ground, it just applies absolutely full braking such that the aircraft would topple over onto its nose. We talked about the payload system, but not giving you a lot of details about it. It consists of two systems. One is a turret, which has got a relatively 360-degree view, lower resolution camera in it that identifies points of interest. And then it's got two very high resolution fixed view cameras that get a really good butchers at whatever it is it's found. So the automatics in this thing are taking the output from the turret, which is performing its search, saying, I've found something. That then inside the vehicle commands the vehicle to fly to a position where you can get a very, very high resolution shot of what you've just found. Once it's done that, then it will flash those images back to the ground and say, I found something, have a look. And at that point, the human interpreter will have a look at it as well and potentially recommand the vehicle to do things like that. This is the system that was looking for the improvised explosive devices when the RAF took it to Afghanistan. And out in the desert, we put some various targets. A calibrated target, and that's the kind of tiny field of view camera that says I found something that looks interesting, and that is then the high resolution camera output for what's coming back afterwards. Similarly, out in the range of things like containers. This is as an alternative to finding sheep. It gives you the kind of views that we're getting from about 5,000 feet. So a typical sortie, we chased most of the sorties as an additional fallback and for publicity purposes. The chase helicopter pilot was a search and rescue guy from Adelaide, ex-Australian Special Forces. We start very early in the morning. This is probably taken about 4 o'clock in the morning, doing pre-flight out in the chill. It didn't rain. The fire brigade put down the water because the photographer said it would make a better photograph. Okay? But again, getting ready to go. And the guys up in the attic doing the pre-prep as well. Off we go. I had the opportunity to act effectively as flight test observer in the back, and there were 2 cameramen chasing the vehicle, and those are the kinds of publicity shots that we were looking for. It had rained by now, and this is the desert going blue underneath. So what did we do? With this vehicle, we did generate a pretty autonomous vehicle that had a high level of operational capability. We were doing automatic target detection. We were sending back real-time satellite imagery from the range at Australia to the United Kingdom, with people in the United Kingdom deciding what they wanted to happen next and commanding the vehicle over satellite link from the UK. We demonstrated that we could fly around pop-up threats, and we demonstrated that we could kill all the links, let the thing strut its stuff, and half an hour later, switch it back on, and it would talk to us and come home. I talked about Western Browns, and yeah, they do occasionally arrive. There is a snake catcher, but these are the 2 of the firemen trying to shoo one away that got itself onto the hard standing. So, if anybody wants to ask any questions or talk, it's your time.
We'll do the others on the side. So yes, fantastic. A fascinating talk. Thank you very much. Hopefully everyone's enjoyed that. We're all out of questions. Thank you to everybody who's joined us on the live stream this evening. Hopefully it's been a good experience for yourselves there. So yeah, I was going to say we've had the round of applause, but yeah, I think thank you very much for taking the time to travel down and talk to us today. It's been a very, very interesting opportunity. So,
you're most welcome.
On behalf of the branch, thank you.